Hi, I'm the Wannabe Coder, and welcome back to the Pac-Man and Python series. This is episode 6, and in this one, we're going to make the game feel interactive by adding pellet collection, scoring, and a simple user interface at the top of the screen. Up until now, Pac-Man could move through the maze and bounce off walls, but the pellets just sat there doing nothing. Now, we're going to change that by letting Pac-Man eat pellets and power pellets, clear them from the screen, and track the player's score as they move through the level. In the last episode, we finally added wall collision detection to the game. We built a function that checks if Pac-Man's leading edge is about to enter a wall tile. And if it is, we stop his movement right at the edge. We also added correction logic to gently snap Pac-Man back onto the grid when the player makes a turn slightly early or late. With collision logic in place, Pac-Man now moves smoothly through the maze and interacts properly with its structure. Let's start by creating the Score and Lives display, the part of the screen that shows how the player is doing in the game. To do this, we'll update our existing renderer.py file, the one where we already have our wall, pellet, and power pellet classes. We're going to add a new class here called UIPen. This class will handle drawing the score and lives at the top of the screen. And instead of just writing the text directly onto the maze, I've decided to draw a simple outlined rectangle at the top of the screen to clearly separate the UI from the rest of the gameplay area. Let's go ahead and switch over to renderer.py and start building it. We'll start with a small addition at the top of the file. We add the following line: from constants import cell size, screen height, and screen width. These values will help us position the user interface elements on the screen, like the score, lives, and UI borders. Next, let's look at a small update inside the pen class. We've added this line: self.color, open parenthesis, quotes, silver quotes, close parenthesis. This sets the drawing color of our pen turtle to silver. You may change it to any color you prefer. Next, let's look at the change we made in the pellet class. We've added a new line: self.stamps equals open curly braces, close curly braces. This creates an empty dictionary, a powerful structure in Python that lets us store key-value pairs. We'll use this dictionary to track the position of every pellet we draw on the screen. Here's how it works. Each time we stamp a pellet onto the screen, we'll store its X and Y coordinates as the key, and the stamp ID that Turtle gives us as the value. This lets us keep track of which pellet is placed where, and most importantly, remove the exact pellet later when Pac-Man eats it. To implement what I just explained, let's go ahead and modify the pellets draw method. Instead of just calling self.stamp, we now write stamp underscore ID equals self.stamp with parentheses. This line calls the stamp function and stores the result, which is a unique stamp ID, in a variable. The stamp ID is just a number that Turtle assigns internally to each stamped object on the screen. We store this number so we can refer to it later, like if we need to remove that specific pellet from the board. Now here's the key line that brings it all together: self.stamps, open brackets, open parenthesis, X comma, Y, close parenthesis, close brackets, equals stamp underscore ID. Let's break that down. We're adding a new entry to the dictionary. The key is a tuple, a pair of values, containing the X and Y coordinates of the pellet. We write that as X comma Y inside parentheses, just like a coordinate. The value is the stamp ID that we just got from Turtle. So we're saying, at this specific coordinate, X and Y, save the ID number that belongs to the pellet we just stamped. By storing that relationship in the dictionary, we now know exactly which ID belongs to which pellet on the screen. This gives us a way to remember where every pellet is drawn, and which ID we need to use later if we want to remove it. We've done the exact same thing in the Power Pellet class. It also has its own stamps dictionary, and uses the same logic to store the position and stamp ID of each power pellet we draw. Now let's take a look at a brand new class we've added. It's called UIPen, short for User Interface Pen. Just like our other drawing classes, this one also inherits from Pen. We'll use it specifically to draw the UI area and display things like the score and the number of lives. We write class U iPen, open parenthesis, pen, close parenthesis, colon. Now we define the function that runs when this object is created. Def double underscore init double underscore with self in parentheses, colon. Inside this function, we call the parent class constructor, super, open parenthesis, close parenthesis, dot double underscore init double underscore, open parenthesis, close parenthesis. This sets up everything inherited from pen, just like we've done in the other classes. Then we write self.font equals open parenthesis, quotes courier quotes, comma 30, comma, quotes normal quotes, close parenthesis. This line defines the font we'll use when writing text on the screen. Courier is the name of the font, 30 is the font size, and normal means the text will appear regular, not bold or italic. Next, we define a method called draw underscore UI underscore area with self in parentheses, colon. This method will draw a rectangle at the top of the screen, which separates the game area from the user interface. Here's how it works. We begin by setting the pen thickness, self.pen size, open parenthesis, to close parenthesis. That gives us a slightly thicker border. Then we calculate the positions. First, we write x equals 0.9 times screen width divided by 2. This gives us the horizontal distance to the right edge of the UI. Next, we calculate the top edge. Top underscore y equals 0.98 times screen height divided by 2. And the bottom edge of the UI box, bottom underscore y, equals top underscore y minus 1.5 times cell size. All of these multipliers, like 0.9, 0.98, and 1.5, are just there to create clean margins and keep the UI slightly spaced away from the edges of the screen. Now that we have all the coordinates, we draw the box. We move the turtle to the top right corner, self.goto, open parenthesis, x comma top underscore y, close parenthesis. Then we put the pen down by writing self.pen down, open and close parentheses. And from there, we draw each side of the rectangle using the built-in goto function and the coordinates we just calculated. That completes the UI outline. Now let's look at the write score method. We write def write underscore score, open parenthesis, self comma score, close parenthesis, colon. This function takes in a parameter called score, which we'll pass to the function later, when we call it from the main file. It will then display the current score on the screen. First, we clear anything that was previously written, self.clear, open and close parentheses. This is important because every time the score changes, we want to remove the old number before writing the new one. Otherwise, Turtle will just write on top of the old text and we'll get a messy overlapping display. Next, we create the message we want to write. MSG equals F, quotes, score colon space, open curly braces, score close curly braces, quotes. This is called a formatted string, and it's a really useful feature in Python. We start the string with the letter F, which tells Python to treat this as a format string. Then, inside the quotes, we can write regular text, but if we include curly brackets, Python will evaluate whatever is inside them. The score within the curly brackets refers to the score parameter that was passed into the method. Now we move the turtle to the spot where we want the score to appear. We write self.goto, open parenthesis, minus 0.7 times, screen width divided by 2, comma, screen height divided by 2, minus 2 times cell size, close parenthesis. This places the turtle a bit to the left of center, near the top. The 0.7 multiplier is there to keep a margin from the edge of the screen. And finally, we write the message on screen. Self.write, open parenthesis, MSG, comma false, comma, quotes, left quotes, comma, self.font, close parenthesis. Let's break this down. MSG is the string we want to write. False means we're not using Turtle's built-in move feature while writing. We just want it to draw the text. Left, in quotes, tells Turtle to align the text to the left of the Turtle's position, and self.font uses the font settings we defined earlier. We do the same thing in the next method, write_lives. This one displays the number of lives and places it on the right side of the screen. Again, we start by clearing whatever was written before, self.clear, open and close parentheses. Then we create the message string. Just like before, MSG equals F, quotes lives colon space, open curly braces, lives close curly braces, quotes. We move the turtle to the right side, self.goto, open parenthesis, 0.7 times screen width divided by 2, comma screen height divided by 2, minus 2 times cell size, close parenthesis. Same vertical position, but now the X value is positive, so the text appears on the right. Finally, we write the message, self.write, open parenthesis, MSG, comma false, comma, quotes, left quotes, comma, self.font, close parenthesis. The only difference from before is that we align the text to the right instead of the left, and that's everything new inside the UIPen class. This class gives us a clean way to draw the user interface, and a simple method to update the score and lives whenever we need. Now that we've finished setting up the UIPen class in renderer.py, let's switch over to main.py and start displaying the user interface. We'll begin by updating the import line at the top. We now import UIPen alongside the other classes. From renderer import wall, pellet, power pellet, UIPen. Now scroll down to the main function, and let's create the objects we need. We're going to use 3 separate instances of UIPen. One will draw the UI rectangle, one will update the score, and one will update the lives inside the main function. In the section where we call the class instances, we write UI_pen equals UIPen open and close parentheses. Score_pen equals UIPen open and close parentheses. Lives_pen equals UIPen open and close parentheses. Each of these is a new object created from the UIPen class. They all behave the same, but we're using separate instances, so each one has its own job. This keeps the code clean and avoids accidental overlap. For example, when clearing text or moving the turtle. Then, when we get to the section where we call the draw methods, and we call the draw method of the UIPen UI_pen.draw_UI_area open and close parentheses. This draws the rectangle at the top of the screen. Finally, we scroll down to the game loop call. We update the line so that it now passes both the score pen and the lives pen. Game_loop with screen, player, score pen, lives pen, pellet pen, and power pen. By passing the score and lives pens into the loop, we'll be able to update them in real time as the game runs. Now let's take a look at the game loop function and update it to draw the UI on screen during gameplay. First, we add the new parameters to the function definition. We add score_pen and lives_pen as parameters to the game loop function. This tells Python that our game loop will now receive 6 objects. At the top of the function, we add 2 new lines to display the score and lives. We write score_pen.write_score, open parenthesis, player.score, close parenthesis. This will draw the current score, based on the player's score attribute. Then we add lives_pen.write_lives, open parenthesis, player.lives, close parenthesis. This shows the current number of lives, using the player's lives attribute. Next, the player moves and checks for wall collisions, same as before. And finally, we get to the onTimer function, which schedules the next frame. Inside that lambda function, we now pass all 6 arguments again, including the score pen and lives pen. All right, Now let's go ahead and run the file. You should see the game window open, with the maze layout drawn in the center of the screen, just like before. But now, there's a new user interface area at the top. You'll see a rectangle stretching across the top of the screen. That's the UI box we created using the draw_UI_area method. Inside that box, on the left side, you should see the score displayed, starting at 0. And on the right side, it should say lives, 3. These values are being drawn by the score pen and the lives pen, which we created using the UI pen class. And because we're calling them inside the game loop, they'll automatically stay updated as the game runs. Now let's switch back to the main file and set up the logic for clearing pellets and increasing the score when Pac-Man eats them. Before we write the pellet clearing logic, we need to make one quick update. At the top of the file, we import one more value from constants.py. We add cell_size to the import from constants line. We'll use this in a moment to calculate the distance between Pac-Man and each pellet. Now scroll down to the main function. We're going to pass 2 additional values into the game loop, player_start_x and player_start_y. Here's why. When the game starts, Pac-Man spawns on top of a random pellet, but we don't want to count that first pellet as collected. If we don't handle this, the player will get free points the moment the game launches, just because they started on a pellet. So here's the plan. We'll pass the players starting X and Y into the game loop. Then, inside the pellet clearing logic, we'll check if Pac-Man is not on the exact starting position before increasing the score. This way, the first pellet still gets cleared, but the score stays at 0 until the player actually moves. Now let's scroll up to the game loop function and add the 2 new parameters, player start X and player start Y. This tells Python that the function will now receive the player's starting coordinates. Next, scroll down to the screen .onTimer call. Inside the lambda, we also add those same 2 values, player_start_x, player_start_y. This makes sure the starting position gets passed into the loop every frame, so we can use it when checking for pellet collisions. Now let's add the logic for pellet collection and explain how it works. One line at a time. We write for, open parenthesis, px, comma, py, close parenthesis, comma stamp underscore id, in list, open parenthesis, pellet underscore pen dot stamps dot items, empty parentheses, close parenthesis, colon. This line loops through every pellet that was drawn and is still stored in the dictionary. If we haven't cleared the pellet yet, it's still considered active. Let's break it down carefully. We start with pellet underscore pen dot stamps. This is a dictionary, stored as an attribute inside the pellet class. It keeps track of every pellet we've drawn on the screen. The key is a coordinate tuple, a pair of numbers, x and y. The value is the stamp ID that Turtle assigned when that pellet was drawn. Next, we use dot items, open and close parentheses. This tells Python, give me both the key and the value for each entry in the dictionary. In this case, the key is a position. We unpack it into px and py, and the value is the stamp ID, so px and py represent the coordinates of a pellet, and stamp underscore ID is the number we'll use to clear it later. Then we wrap the whole thing with the word list, followed by open parenthesis, and we close it with a closing parenthesis. This creates a temporary list copy of the dictionary's contents. Why do we do that? Because we're about to loop through the dictionary and remove items from it at the same time. If we did that directly, Python might crash or skip over some of the entries. That is because dictionaries are designed to stay stable during a loop. If you start modifying the dictionary, like deleting entries, while Python is still in the middle of going through it, the structure of the dictionary changes under the hood. By making a list copy, we can safely loop through all the pellets, even as we clear them from the dictionary one by one. So altogether, this line means, for each pellet currently stored in the dictionary, get its X and Y position, and its stamp ID, and loop through them safely, even if we clear them while looping. Now let's move on to the if statement inside the loop. We write, if player.distance, open parenthesis, px, comma, py, close parenthesis, is less than cell size divided by 2, and open parenthesis, px, comma, py, close parenthesis is not equal to, open parenthesis, player underscore start underscore x, comma, player underscore start underscore y, close parentheses, colon. Let's break that down. We're checking two conditions: that Pac-Man is close enough to the pellet and that the pellet is not the one he spawned on. Let's start with the distance. Player.distance, open parenthesis, px, comma, py, close parenthesis. This uses Turtle's built-in distance method. It calculates how far Pac-Man is from that pellet's position. We compare it to cell size divided by 2. This ensures the collision is detected when the distance between Pac-Man's center and the pellet's center is less than 15 pixels. Next, we check the second part of the condition. This compares the current pellet's position to the coordinates where Pac-Man spawned at the start of the game. If they're different, we allow the score to increase. If they're the same, we skip the points, because that's the pellet Pac-Man started on. So the full if statement means, if Pac-Man is close enough to the pellet, and it's not the one he started on, then treat it as collected. When that happens, we remove that pellet from the screen. We do that in 2 steps. Step 1, clear the pellet stamp. We write pellet underscore pen dot clear stamp, open parenthesis, stamp underscore ID, close parenthesis. This tells Turtle to erase the specific stamp with that ID, which is the visual drawing of the pellet at that spot. Step 2, delete it from the stamps dictionary. We write del pellet underscore pen dot stamps, open square bracket, then inside parentheses, px, comma, py, close square bracket. This removes the pellet's entry from the dictionary, so we don't keep checking or interacting with it later. By clearing the stamp and deleting the reference, we make sure the pellet is truly gone, both from the screen and from our internal tracking. Now that the pellet is removed, let's update the score. We do this with a simple line, player.score plus equals 2. This increases Pac-Man's score by 2 points every time a pellet is collected. Next, we write elif player.distance, open parenthesis, px, comma, py, close parenthesis, less than cell size divided by 2, and open parenthesis, px, comma, py, close parenthesis, equals, open parenthesis, player underscore start underscore x, comma, player underscore start underscore y, close parenthesis, colon. This line checks if Pac-Man is close to a pellet, and that pellet is at the player's starting position. If both conditions are true, we clear the pellet stamp and delete it from the dictionary, but we don't update the score. Now let's move on to power pellet collection, and this part is almost identical to how we handled regular pellets. We start with 4, open parenthesis, px, comma, py, close parenthesis, comma, stamp underscore ID, in, list, open parenthesis, power underscore pen.stamps.items, open and close parenthesis, colon. This loops through all the power pellets on screen. Then we write, if player.distance, open parenthesis, px, comma, py, close parenthesis, less than, cell size divided by 2, colon. If Pac-Man is close enough to the power pellet, we clear the stamp, delete it from the dictionary, and increase the score by 50 points. Next, we give Pac-Man a temporary speed boost. We write player.move underscore speed plus equals 3. This makes Pac-Man move faster, which is a fun reward for collecting a power pellet, but we don't want him to stay fast forever. So we schedule a reset using screen.onTimer, open parenthesis, player.reset underscore speed, comma, 3000, close parenthesis. This tells Python, wait 3 seconds, Then call the player's reset speed function. We don't need a lambda here because we're not passing any arguments. We're just calling a function by name after a delay. We haven't created the reset speed function yet, but don't worry. We'll define it right after this so it resets Pac-Man's speed back to normal. Now let's switch over to actors.py so we can set up the reset speed function. We scroll down to the bottom of the player class in actors.py and write def reset underscore speed, open parenthesis, self, close parenthesis, colon. Inside the method, we write self.move underscore speed equals player underscore move underscore speed. This function resets Pac-Man's speed back to the value defined in player move speed in constants.py after the temporary boost from a power pellet. Great! Now that everything's in place, go ahead and run the file. You should see your Pac-Man game start up with walls, pellets, power pellets, and score tracking. Move Pac-Man around the maze. You'll notice that when he collects a regular pellet, you get 2 points and the pellet disappears. When he collects a power pellet, you get 50 points and he speeds up for 3 seconds, then slows back down just like we planned. Alright, let's do a quick recap of what we accomplished in this episode. We created the user interface class and used it to draw the user interface area and display Pac-Man's score and lives. We added logic for pellet and power pellet collection, so now Pac-Man can actually eat things. Each regular pellet adds 2 points to the score, and each power pellet adds 50 points. We also added a temporary speed boost that kicks in when Pac-Man eats a power pellet, and then resets after 3 seconds using a new method we wrote called reset speed. And of course, we updated the display so the score shows up in real time. That's a big step forward. Now in the next episode, we're finally going to create our enemies, the ghosts. We'll start by adding them to the maze, give them basic movement, and set the stage for more advanced behavior later on. It's going to be fun, so don't miss it. If you found this helpful, a like and subscribe would really help support the channel, and make sure you don't miss what's coming next. I'm the Wannabe Coder. Thanks for watching, and I'll see you in the next episode.